In the previous sessions, you've heard about data science and machine learning and the different use cases you can address with these technologies. In this part, we'll cover a complementary technology to machine learning, which is graph analysis. My name is Hans Fiemann. I'm the product manager for the Spatial and Graph technologies in Oracle. I'm covering the region of Europe, Middle East, and Africa in particular. Anytime you're using your GPS device in the car or mobile phone with Google Maps on it, and you're trying to find the shortest path from one location to the other, you're essentially using graph databases or graph technologies. That is because the road network as we know it can be or is being represented as a graph in the underlying technologies in order to find the shortest path between two places, which would be essentially represented as edges, as we say, connecting the different points, the points being corners on the road network or intersections on the road network, and the edges being road segments connecting them. Graphs can also be used for a variety of other purposes. In fact, graph analytics have primarily been associated with social network analysis, for example. And I have a little example here, which does not only look at the connection between characters, and in this case, these are characters from Game of Thrones, or to be precise, from one of the books of Game of Thrones, but they are also being used to look at the interaction between characters in a multitude of other ways. Graph algorithms can use the connections, the relationships between characters in an automated manner to find out communities, like in this case, and also to find the most important character inside of this community. And importance can be defined in different ways, so there are different algorithms for different types of importance. Graph analytics and graph technologies actually have become very popular, and that's also reflected in the analyst's opinion. So if you look at the top 10 data analytics technology trends for 2019, which Gartner came up in spring of 2019, among these top 10 trends, trend number 5 was graph databases and graph analytics. What's made graphs so popular is what I already mentioned. They are very easy in terms of modeling. And already from looking at it, you can derive information. The key thing, however, also the key differentiator compared to relational technologies is that graph technologies allow you to do different kinds of analysis which in relational technologies are either very cumbersome and slow or impossible altogether. And what's more, and I'll touch on that later on, you can use it as an additional signal for machine learning. So it can become complementary for machine learning projects, refining the results by having an in-depth look at relationships, particularly if we're talking about relationships over multiple hops in the graph. Typical examples for graph analytics would be community detection and influence analysis, as I was trying to explain in the context of the Game of Thrones example, which you would, for example, find in churn risk analysis in telco or in HR turnover analysis and so forth. Graphs are very useful also for product recommendation, right? Looking at the similarities, at similar behavioral patterns between customers. And if you can find similarities, then of course you can also use the same technique to find those customers, individuals, whatever it may be, objects, which are particularly different. So you can use these techniques also to find the outliers, to do anomaly detection, like in the case of social network analysis. You can, for example, use that to find spam or sock puppet Twitter accounts and the like, or you can use it for fraud detection in healthcare and so forth. Then, of course, there's the conventional path analysis and reachability, which is kind of like what I tried to explain in the road network example, which you don't only apply to road networks or utility networks, but you can also use that in the context, for instance, of large connected data sets such as the Panama Papers. Yeah? You may recall the Panama Papers, where you would have individuals connected to the bank accounts being associated with companies being associated with directors of that company, and maybe one of the directors is the wife of the first person in that network. So these kinds of relationships, looking at whether there's a connection over multiple hops between two people or two entities of some sort, can be very relevant for the purpose of fraud detection, criminal investigation, tax fraud, and so forth. Plus, in graph analytics, you would also find the topic of pattern matching. Again, something where you would, for example, look for circular payment patterns in financial transactions, which are indicative of money laundering, for instance, and so forth. Customers in this space include, for example, financial services companies. One of my favorite examples is a customer of ours from Bulgaria. They are part of a large international group, companies called PaySafe. They provide online payment solutions like e-wallets. They have two brands. You may have come across Skrill or Netella as brands for e-wallets. They're actually a significant payments provider. They process of the order of 500,000 payments every day. And as you can imagine, these kinds of online payment services and e-payment services are susceptible to fraud, because you can open accounts relatively easily, and you can transfer large amounts of money in small chunks, for example, relatively easily and inexpensively, so that it is popular with anyone interested in money laundering and so forth. So as companies such as PaySafe are mandated to analyze any kind of transaction for potential fraudulent behavior, they have implemented a number of technologies in order to counter fraud. At the moment, they're primarily using our technologies for real-time, for transaction monitoring, then investigating whether a transaction is suspicious or not on the basis of either a rules engine, that's what they conventionally had, or increasingly also looking into machine learning techniques for that purpose. Here are just two types of example of financial transactions which the PaySafe team has been finding in their data sets. On the left-hand side, you can find every vertex in this graph here is an e-wallet, and every edge is a financial transfer. So here you can see on the left-hand side an e-wallet which is being used to transfer money from the left-hand side to the yellow account on the right-hand side, but the transfer doesn't happen directly, but indirectly through some 50 intermediate accounts. So clearly this shows that there's somebody who wants to hide something. On the right-hand side, you have a way more complex example, which is a lot more difficult to figure out, where in effect you have one source of all financial transfers, and basically by and large only one sink where all the money ends, but it goes through many, many intermediate steps, which is just indicative of somebody trying to hide a financial transfer in large amounts of data. And these are the kind of things which basically all financial institutions are struggling with, and trying to use different techniques to address this kind of fraud. Conventionally, this has been, and this is the same case for PaySafe, this has been based on a rules-based approach, where the rules engine essentially takes the decision to process or not process a payment. However, if you just use a rules-based approach, you're not particularly flexible, and you're missing out on all those cases where collusive crime plays a role. And that's why the PaySafe team relatively early on has decided that the only way to address this problem properly is through a graph database. And as I said, they're increasingly complementing this technology with machine learning. Before I explain how graph analytics can be used in conjunction with machine learning, let me just quickly go over one example of using plain graph analytics for the purpose of anomaly detection, such that you can get an idea of how this can be used in basically in any kind of scenario where relationships play a role. The example I have here is the healthcare industry. It's basically healthcare billing data, and I'll just use that to show you a couple of fundamental concepts in graph analysis, which we will make use of later on in the machine learning part. So in this healthcare billing data set, what we have is all the medical service providers, so essentially all the doctors, and all the services they deliver. If we want to find out doctors who are doing things which are, in the wider sense, out of the ordinary, one approach we could take would be to look at the specialities of a given set of doctors, say neurologists or cardiologists, looking at the typical services these cardiologists provide, and then try to identify those doctors which are not cardiologists, but provide these kind of services. And that's what we've been trying to represent here on the right-hand side, right? We have the 900,000 doctors, we have some 6,000 different types of services they perform. Whenever a doctor performs an operation, or whenever a doctor provides a certain service, we create, if we group the doctors into their different specialities, suppose we have all our cardiologists here in green, the service they typically provide, we have all the links between the cardiologists and the services. Now, if we have a doctor here who's not a cardiologist, but providing mostly services which only cardiologists provide, that will be suspicious. For example, in this case, in order to find out those doctors which are close to the cardiologists, but which are not cardiologists, what we can use is a predefined, well-known, well-documented algorithm called personalized PageRank, which helps us to find outliers. We can use this concept of closeness to distinguish between those entities which are close to the starting set and those which are far away from the starting set. And that helps us in the anomaly detection, which I was using here in this healthcare data set, to identify, first of all, from the doctors in the starting set, to identify the services which are close to the starting set, which are the services which are performed by the starting set many times, which are typical for the starting set. So that would be the specialty actions, in this case maybe for the cardiologists. And it also allows us to find doctors which are close to the starting set. And this indirect one hop to the service to the doctor, that gives us a measure for how similar a doctor is to the starting set. This closeness can then be used to figure out, okay, if this is not a cardiologist, then if he is close to the cardiologist, we may want to look into that in more detail, right? The main reason why I've tried to explain this was that we can make use of this concept of closeness as one possible metric, which you can use in conjunction with machine learning, right? If you have your graph and you compute some metric reflecting this closeness, or other metrics for that matter, but just to stick with the example of this closeness to a starting set, we can build a predictive model on the basis of that graph metric, run the neural network, the convolutional neural network, or whatever you have already been looking at in previous parts of this course, and then use this model to score and classify data. And potentially we could even feed that, the output from that machine learning back into the graph. There's a lot more information in a graph, captured in the graph, which you can make use of. But as you've already learned, as an input to your machine learning model, you need something which is a numeric representation of what you're looking at, right? No matter if it's an Oracle machine learning, if you use Oracle machine learning as the platform, or if you use the machine learning capabilities in datascience.com, no matter what kind of platform is your favorite platform, you need a representation of the graph. You can use the closeness on its own. That would already be a possible signal. And you can use other graph metrics, be it the regular PageRank value, be it between the centrality, be it there's loads of possible metrics you can derive from a graph, which would help to describe the graph to some degree. Now, does this technique work? Well, let's look at an example. Let's look at an example. We have, again, used a practical example, in this case from student classification, where basically the question was whether you can predict a student's major or a student's department just by looking at the classmates in the course that he or she is taking, right? So we have a data set where we have, again, a graph which has the students on the one side, we have the courses on the other side, we have this student taking that course, this student also taking the other course, this is a student which is labeled, so that's a computer science student in this case, taking this course, that course, and this course, and so forth. And on the basis of this data set, we essentially did 4 things. We compared the outcome just to see how accurate the predictions are. First thing we did was we trained a neural network on the standard features. So for every student, for example, we had the student's age, we had, of course, the courses which the student took, we had the gender, we had all this kind of standard information. Also on the courses, we had additional information. In fact, we used entity recognition to figure out from the course description what the keywords are and so forth. So we used this convolutional neural network to figure out, to predict on the basis of the labeled data set which we have here, what students are associated with which department. Then we took a plain graph analytics based approach where we tried to predict the department using the personalized PageRank algorithm, which I was referring to earlier in the healthcare example, and figure out the highest scoring vertex from that, and then combined all of these features. And the interesting result was, first of all, the convolutional neural network, of course, needed training. So in this case, we used like 160 iterations on the data set, and we reached an accuracy of about 0.52, 0.53, roundabout. The plain property graph algorithm, of course, didn't require any training because it's a deterministic algorithm. We got an accuracy of 0.72. Now, if we go back to the example, why is this? Now, if you look at what the neural network took into account, like the features of each student, the features of the courses, and the information which student was taking which course, that was missing out on a certain set of information. For example, if we take this student, the machine learning knew this student was taking that course. However, it did not take into account that this student who took that course was on the same course as that student who took this course together with that student who took this course together with that student. These multi-hop relationships are very important, apparently, because they give us way better results, as you can see from the personalized PageRank algorithm. So whenever you have a problem where relationships play a role, you may want to consider graph analytics, and then you don't even need, you don't necessarily need a convolutional neural network approach in order to get pretty good results, right? We then, as I mentioned, combined the approaches. We used the deep walk, and then, of course, had to do training and got to a decent level of accuracy. Not quite the accuracy of the personalized PyTrank. And then only if we combine everything, like the neural network on the original features and the graph features, then we would be a little better than the plain personalized PyTrank. Right, so bottom line here is you may want to have a look at graph analytics as a technique if you have data sets which are interrelated in some way, shape, or form, or you have multi-hop relationships playing a role in it. I hope I've given you a couple of examples in the use cases earlier on. So just to wrap up, what's this to do with Oracle? Well, Oracle has property graph support and has had property graph support on all three platforms, being the database, the big data platform, and the clouds, the Oracle Cloud Services. We are working on the basis of an analytics engine which is using the database, the Oracle database, or Oracle NoSQL, or just plain HBase as the storage layer, and then for the purpose of graph analytics, load the graph into the analytics engine for running these algorithms in this in-memory analytics engine in parallel. The key thing for us is to have the dedicated storage structures which we need to run these graph algorithms efficiently, and that's what we only have in the dedicated engine, which we can then control by means of scripting or through APIs, be it through Java, through Python, through REST, or using tools like visualization tools which are integrated with this platform. In summary, I hope I've given you a little bit of an idea of what graph databases and graph analytics can be used for. Right? These graph databases are not designed to replace every relational database on this planet, but they are particularly good at analysis of any data sets in which connectedness, or in the technical sense, graph topology, plays a role. And graph analytics can give you a lot of new insight into especially relationships, dependencies, behavioral patterns, and the results in turn can be used nicely to refine your machine learning platform, or it can be used as an input to your machine learning platform. Right? For us in particular, as Oracle, what we provide is a property graph platform, which has not only a comprehensive set of analytics included already in the product, including some 58 pre-built graph algorithms, but we also use this scalable, parallelized in-memory analytics engine, which I was referring to, which is just extremely fast because it's wholly in memory. It is integrated nicely with the relational database, but it can also work in conjunction with Spark, with R, or it can be used on the Hadoop platform using HBase as the storage layer, as well as the Oracle database as the storage layer. If you want to use these technologies, try them out in an Oracle context, you can find that you can use, for example, the Oracle Cloud Services for that purpose. We are, and that's futures, I have to say, we are currently working on a managed graph cloud service. That will only be later available, hopefully sometime later this year. But if you want to get started now, you use, for example, the Oracle Data Warehouse free tier as the storage layer, in conjunction with the Java, in-memory analytics engine running in a Java runtime environment, which connects to it to perform graph analytics on the basis of data which is sitting in the autonomous data warehouse. I hope you found it useful. If you have any comments or feedback, feel free to reach out to us. Thank you for listening.